So I'm sure that if you've done the numerical RTA workflow as a part of Whitson Plus, you've been able to see all these different type curves in the Bowie diagnostic plot. And also, if you read Braden's original paper, you've seen all these different type curves associated with the different tank sizes, essentially. Um, and in short, the difference between the different type curves and how they're generated, all of them are generated with a numerical model. All have the same fluids, same geomechanical properties, fracture connectivities, etc. The only difference that we're changing between the type curves is the size of the tank itself. So when you have the actual production data generated with the so-called infinite acting model, and you generate these different type curves, you only run the model with the same constraints and assumptions. The only difference is that you're reducing the tank size itself. And each of these individual tank sizes, they generate a different type curve. And of course, a smaller tank size will see boundary effects sooner and vice versa. So that allows you to have essentially all these different type curves overlaying the actual production data, and you're left trying to interpret an A root K and picking the closest type curve which has an associated OIP or OGIP number associated with it. So how do you actually decide how many type curves you're going to show in Whitson Plus and the relative size of those type curves? And that's what this video is about today. So at the top here, you can essentially say, I would like to show 5 or 10 different type curves. The only difference between these two is if you want to run 5 models at the same time or 10. All these models are essentially run in parallel on the cloud. You can run either 5 of them or 10 of them at the same time. 10 of them, then you're running 10 of them in parallel. If you're running 5, you're running 5. But then we also have these different options here, which says 5 smaller models and 5 larger models. And what does that really mean? Well, it just means that they're smaller or larger compared to the base case. Okay, and the base case will essentially yield boundary effects, which you see here of the highest type curve, which in this case is this guy right here that's behind the observed data at around 200 days, which is not uncommon for more modern, well, at least that being fairly conservative. Okay, but let's say you have some edge cases that either have a very, very tight completion or a very, very conservative completion, such that you're either going into boundary dominated flow extremely fast, such that you would require actually smaller type curves than what we're seeing here, or something that's in boundary for a very, very long time. What do you do then? Well, then you simply go ahead here, change to either smaller or larger type curves, and you click run. And just to show you very fast here the relative difference, here we see all these different type curves for a set of input parameters. If we go in and change these to what is essentially larger type curves, that's what we have here, 5 larger type curves. They are going into boundary much later. So we see the smallest type curve is like 10 BCF. And the highest one is actually close to 80. So now we see that these type curves compared to the base case have been shifted basically up and to the right. That's what we're seeing right here. Okay, so everybody sees that the type curves go into boundary later. The LFPs themselves are still the same. They shouldn't change. But what if we do the opposite, that we want something that goes into boundaries sooner? Then we would like the type curves to essentially start and fall off from the straight line even faster. And that's what this smaller type curve option is right here, where we see in the highest OIP stem or OGIP stem here is 13 BCF, which would not be actually large enough for the case that we're studying in this case. Okay, so that's the only difference between these different options right here.